record. Yeah. Okay. So yeah, so basically what Z3 is that it is something that will take some expressions, so some bunch of expressions that can be Boolean, int, whatever. So it's an expression that can have multiple different kinds of types, etc. Right? And it will take some formula made of these expressions, and it will give you whether this formula has a satisfying assignment or not. That is to say, whether we can in some sense put some values of the variables in this expression so that this expression actually evaluates to true, right? So an example would be if I say something like, say I've got two variables and I say something like x greater than 0, right? And I say something like, say, y times x is equal to, let's say, I don't know, y, right? So this together, if I give you this sort of a formula, right, this got two variables, and for any given particular like combination of values of these variables, this will be either true or false, right? What I'm asking you is there some combination of value of these variables for which it will be true? It's kind of like SAT, but in SAT we just have bools. So here in SMT we have other kinds of variables as well. We can have ints, and we can have things like real numbers. You can have even bit vectors, arrays, some things like that, right? So Boolean formulas of these kinds with variables of various different types, and associated operators as well. So this collection of what types this variable can be, what the operators are, these are called theories, right? Yeah. Anjali has joined. Okay, so yeah, so these are called theories, and what SMT solver will do, it will take a huge expression in like multiple variables with various types. It can also be mixed types. You can say that x is a real number, y is an integer, or something like that, right? And it will give you a satisfying assignment. So for example, if you pass this to SMT solver, it might give you something like, say, x equals 1, and let's say y equals 2, right? Whereas on the other hand, if I had said something like y times x equals to 0, then it would have been giving me, say, x equals 1, and then y would have to be 0, right? So something like this. So SAT solver will take this expression and give you a assignment for the variables for which it is satisfiable. So SAT solver does that for Boolean variables, sorry. This is only for bools. And the SMT can do other types as well. So this is more general, let's say. Right? So this is the basic idea for SMT solver. Another thing that SMT solver allows you to do is it also allows you to do first order quantification, which means quantifying over the values of the variable. So you can even say something like, say, if I can have an expression like this, for all x, I can say x greater than 0 implies, let's say, y dot x equals y. So this is also another expression that I can pass to the SAT solver. So again, this will give me, so here there's only one variable, there's only one free variable, which is y. So it will give me something like y equals 1 as the assignment, right? Okay. So Anleeb's here. So just so you know what's going on, sir had some issues, so he had to step out for a while. So he has asked me to continue from the Z3 tutorial from before. So I'm giving a quick 5-minute intro for Z3, and then we'll move on to other things. Okay, so this is basically what Z3 is. It'll, or in general, what SMT solvers are. So it'll take expressions which can have int, bool, etc., types, various operators, and you can have first order quantification, that is quantification on x. You cannot say like for all sets of x such that and so on, but you can say for all x and such that, right? It will take such an expression and it will try to give you either an assignment for which this expression evaluates to true, or it will try to give you a proof that this expression is unsat, like there is no such assignment, right? Or it can also just fail. It can also just say, I give up. So it can give up. So this is what an SMT solver in general is. And Z3 is a particular SMT solver which comes from Microsoft. So is this, as a 5-minute intro, is this clear as to what Z3 is and such? Any questions?
Just one question. Okay?
Yeah.
So in ours, when we took NCSV, we were also introduced to this push pop feature of Z3.
Yeah. Well, I'll talk about that. Yes.
Okay, fine. Yeah, I thought I was confused whether it's a part of Z3 or is it some additional API that people use?
No. It is a part of Z3. It is in fact it is a part of SMT-lib2 as well. So yeah. So most cool. Things support it. Yeah. I mean, of course, you can have solvers that don't, but like most do. So yeah. So is there any questions at this point? Otherwise, I'm going to just move to this thing, showing you some code for Z3.
Sure.
All right, so let's look at some code. So this is some code that there was in this tutorial, and I've just added some comments and such. I'm going to make this a little bit bigger. So let me actually quit this and say mod to counter SMT2. Okay, so there's two ways of using Z3. So one is this via the SMT-lib2 interface, and the other is via the Python interface. So the SMT-lib2 interface basically looks something like this. So SMT-lib2 is this standard language which all SMT solvers use, via which you can do things like define what expressions you want to pass to the SMT solver and such things. So let's just check whether there is a simpler thing for this. Yes, it is this thing. So let me open that one. Yeah, not this. Yeah. So this is what like a really simple piece of SMT-lib2 code looks like. Is the zoom okay? Can everyone see this font? This lower terminals for now, don't worry about that. Just this main thing.
Yeah.
Yeah. Okay. All right. So basically, SMT-lib2, the first thing you need to know is that it's a Lisp-like thing, right? So the way the syntax works is that you have brackets, then you'll have the function name, and then you have space-separated list of arguments, right? So for example, if you look at just this part, instead of saying x is less than y, you say less than applied to x and y, right? And you don't have any commas. You just say less than space x space y. So this basically means x is less than y, right? Similarly, if you wanted to say y plus 1, you would say plus y1, right? And if you wanted to then say that x equals y plus 1, then you say equals x and then within brackets this and that, right? So this is a prefix syntax, which is in a style similar to what Lisp uses, right? So it might be a little like sort of weird at first, but I mean, it's intuitive once you use it a couple of times. Okay. Yeah, so let's go over this from top to bottom and see what's going on. The first thing that we need to do is declare our variables, right? So what are the variables that our various expression is going to involve? Now, in SMT-lib2, there is this thing called declaring a function, where you declare an uninterpreted function. What that means is that that particular function can be whatever. And the SMT solver's job is to determine what that function is, right? Now, variables are actually special kinds of uninterpreted functions that don't take any arguments. So, I mean, what basically we are defining variables to be zero-array functions, right? So variables are functions that don't take any arguments, and then we'll give you an output of some type, right? So for example, x is a variable, but what we're saying is, okay, we're going to declare a function called x, which does not take any arguments and returns an integer as an output, right? So this declare syntax basically says the declare function name, and then over here you'll have the list of the types of the inputs. So you can say things like, say, int bool. That would mean that you have two things as input, the first one being an int, the second one being an bool, and then the output would be just an int, right? But since we want to say that it's a variable, we're going to say that, okay, it's a zero-array function, which means there are no inputs and the output is just an int. Similarly for y, and then we build out two expressions, right? So notice this command. This is called the assert command. So what you do is basically what happens in any SMT solver is keeps track of various assertions that you can add to the solver. And at the end of the day, it's going to check whether all of them together can be true, right? So here we are asserting two things. And again, this is like infix syntax, but what we are asserting is basically x is y plus 1. And we're saying that x is also less than 1, right? So now when we assert these two things, inside the solver, there's a table which will contain these two expressions in some internal format, right? And then if we just call checksat, the brackets outside is important because checksat is a function that you're like calling with no arguments. So if you call checksat, then what the solver will do is it will look at, okay, what all has been added by asserts, right? It will take all of those and take the conjunction of them and check whether that entire huge formula is satisfiable or not. So in this case, it will check whether this and this is satisfiable or not. That is there some value of x and y for which both of these are true, right? So that is what it's checking. Okay, now I'm going to go to the terminal here. So let me do this.
The terminal could be larger actually.
Yes, I'll make it big. Yeah. Right. So in fact, let me just quit out of this. Yeah. So okay, so basically now let's run this thing. So the way you run this, run a SMT lib2 file with Z3 is just once you've installed Z3, then you just do Z3 and then pass the SMT lib2 file. Simple input SMT. Right. Okay. So let's look at the first line of this output, right? So this output says unsat, right? So this corresponds to this line 12 here. So what it's saying is that, okay, when we're checking the satisfiability, this is unset. And that makes sense, right? You can't have x is y plus 1 and then also say x is strictly less than y, right? That doesn't work. So that is going to be unset. If on the other hand, we say something like, say, x is less than equal to y, then it'll be sat. So if we do this now, oh, sorry. Did I not save this? Okay, even that is not what I'm missing. Okay, so instead, let's just say something like, let's make this 0. I see. I'm being dumb. Sorry. I mean, of course, if you make this 0, it's still unset, right? You're still saying like x is, if you still say that x is y plus x is equal to y, and then you say x is less than y, those are two things that cannot be sat together, right? Yeah, now it says sat. So this first line output with respect to this is sat. Also, another thing you can do with Z3 is that you can pass this get model command, and then what it will do is basically, if it is satisfiable, it will give you the values of x and y for which the two formula are true, right? If it is unsatisfiable, this get model command was throwing an error. That's why whenever we are seeing unsat before, this error was coming up, like line 15 column model is not available, because if it's unset, then there is no satisfying model, right? Yeah, go on.
Yeah, if I just ask a get model instead of doing a get check sat before, is it still going to give me a model if it's sat?
No. It's going to still say that model is unavailable. So for example, if we comment this, it's going to do this.
Yeah.
Right.
I see.
Yeah.
So it generates a model as part of the checking sat thing and then just prints out the get.
Right.
Get model.
Yeah. With get model, you just print it out. And I mean, there is some pretty printing and such also, like some stuff like that. But yeah, basically that's the idea.
Thanks.
Yeah. So this is the basic usage of Z3 via this SMT2 sort of a thing. And okay, so just looking at the model, I mean, the model that we have gotten, it's again in this list-like format, but what it basically sees that let's define y as 0 and let's define x as -1. And that works, right? So -1 is less than 0 and -1 is 0 minus 1. Okay. Yeah, of course, I mean, I could have also done this, just so you know that it's not something that you have to do. Just do the same thing. Yeah, so any questions so far?
Can you do something fancy as well?
Yeah.
Like, where, I mean, obviously you can, like, can you show that like x square plus y square or something like that?
Sure. Sure. So give me an expression then.
X square plus y square equal to 1.
Sure. Okay. So let's say 1. And then we'll have this entire thing. And again, plus is not gonna be here. I was instinctively writing it there, but yeah.
I think you've got
one bracket. Yes. Yeah. So this is x square plus y square equal to 1. Let's just delete this comment for now. And then what else do you want? Do you want something else?
Yeah, I guess this x less than y is good.
Okay. And remember that x and y are ints. So let's see what happens.
Oh, yes, I forgot.
Oh, where? All right, another bracket. Yeah, y is 1, x is 0. That works.
Nice.
Right. I mean, you can I don't know what this will give. I'm not. Yeah. Okay. Sure. That also works.
Can you make it 3 or like something like 1,000?
Now it's unset. 3 is unset.
Nice. Can you make it something bigger?
Yeah. I mean, okay. So as far as I understand, if you make this number bigger, it shouldn't like make this thing more difficult or less difficult for Z3.
It's using some other things solve, right?
Yeah. So Z3 mainly it gets hurt if you have too many variables from what it seems. Right. So now let's look at something that is a little bit more complicated, not just in terms of these expressions, but like as a thing in itself, right? Okay. So what we have here is basically we're trying to encode this mod 2 counter, and I went over this in some detail. I'll just not go over the expressions itself, but I'm just going to give you the syntax that's going on over here. A mod 2 counter basically has got it's going to have two bits in its state, right? And in each iteration, it's going to just add 1 to this 2-bit integer, and once it reaches 3, it's going to wrap back around, right? So we're going to represent this as a transition system, which means that we want to represent the init and the trans as Boolean functions in some sense, right? So given a state is the initial state. We want to define that. So that is again done over here. So this command called define fun, right? This define fun is again going to take the function name. It's going to take the function signature. So it's going to basically take some formal variable names, like say x0 is a bool, x1 is a bool, and so on. It's going to take the output, like the return type, so function signature return type, and then you're going to have the exact function expression. So it basically takes x0 and x1 booleans as input, gives a boolean as output, and what is this boolean? This boolean is going to be this expression, and it basically says that x0 and x1 are both 0. Similarly, you can define a transition relation as taking 2 states, right? That will be 4 bits. And then I've just done a case bash over here. You'll have to do it in terms of ands and implies and so on, but basically this is just a case bash, right? So we can define the init and trans like this. We can again declare all of our variables as before. So I've declared 4 variables corresponding to 2 states, right? So x00, x01 is basically the 0 and 1 bits of the first state, and then basically x00 is basically 0 for the first state, x01 is 0 for the second state, and similarly this is 1 for the first and second state, right? Okay, so now what we want to say is that these 4 variables, specifically x00, x10, and x01 and x11 form a path, right? Like a path of length 2. So to say that we should say that this thing should satisfy init, and then these entire 4 things should satisfy trans. So let's assert those 2 things. Right. So so let's, before we go here, just ignore this push and pop and such things for now.
Just a quick question, like assert init x0, 0 and x1 means that all of them are 1?
No, all of them are 0. So that is how we have defined init here.
Oh, okay.
Yeah. So if you look at basically what it says is that apply init on like these variables, and then the result should be like
okay, both
so,
of them are 0. Okay.
yeah. And this is like and of not x1 not x0. Yeah, both of them are 0.
Mm-hmm.
Yeah. Similarly, we are
Okay.
saying that trans. So trans just encodes this addition mode 2 basically.
Okay.
And again, I've just done a dump case bash. There's probably more smart ways of doing this, like you can instead of doing a
Yeah.
case bash, but yeah, that's what I've done over here.
Okay.
So yeah, we're asserting these two things, right? Now let's say that this is a program that you had and you have like encoded this in this way, and that you want to check this condition, right? Like after one step, is it possible that we reach the counter value 2, right? So to check whether that is possible or not, let's add that in as an assertion as well. So we are saying that, okay, x00 is an initial, like x00, x10 represents an initial state. And then from x00, x10, we have taken a step and gone to x01, x11. And now we are saying that, okay, the state x01, x11 actually corresponds to the counter value 2. So we are saying that x11 is true and x01 is false. So that's basically 10, which means counter value of 2, right? So you're saying that, okay, this state corresponds to a counter value of 2. So these three assertions together, what they say is that basically in this particular program, in 2 steps from a valid initial state, we have gone to a state where the counter value is 2. Now, if you think about a mod 2 counter, this should not be possible, right? I mean, this should actually be unsat. So let me just comment these out so that these are not in the picture, right? So this should give me an unsat, and let's check whether that happens. Yeah. So yeah, this gives me an unsat. Any questions so far? This is a good point to ask questions, I think. No?
Yeah, I had a quick question. Like, yeah, like for SMT solvers, like, like you had said a long time that there are some islands of like things that are more tractable. For example, like these Boolean formulas
Yeah,
are better.
these are determinist, like decidable. Sorry.
Yeah, these Boolean formulas are in some sense better than SMT ones. So, like, how much? Let's say you can scale SMT like variables to, let's say, n variables. So, how much can you do the same for Boolean variables, like 10x, 20x, or what?
Oh, okay. So I think in terms of SMT, I've definitely seen places where people have used, say, millions and then Boolean variables, the same order of magnitude. So I'm not sure if there is like if it's a simple case of, you know, just if you use Boolean variables, it'll be a 10x more variables you can do in the same amount of time. Certain SMT logics are actually even faster than Booleans. So one example is this LRA is faster. LRA, the most amount of time actually is spent encoding this thing into their internal thing. But once you do that, it's a simplex, right? Which is like faster than a SAT solver.
Okay.
Yeah, so it's more, a little bit more like complicated than that. I won't be able to give you like a rule of thumb answer in that sense. Also, I mean, it depends on the solver as well. But even for Z3, I can't give you this thing. But you can try it out, like try out a few formulas and see what you're getting.
Okay.
Yeah.
Yep.
Yeah. So any other question? Also, I think this thing is. So is there a timer that you guys are seeing, and is it going to kick us out? Because if that's the situation, again, because sir couldn't start the meeting today, this, like, we tried, but I couldn't get a license for this one. So
8 minutes.
8 minutes, right? Okay. Yeah. So are there any questions? No. Also, Chandradeep, was the introduction okay for you? Are you following so far?
Yes, it's fine.
Yeah. Okay. Sure. All right. So I'm just going to assume that there are no questions. I'm going to talk quickly about this push pop thing, and then we'll have to, I'll send out another Moodle message and another message on the WhatsApp group, and we'll basically start another meeting, right? Is that okay with you guys? Give me a yes or no.
Yep.
Yeah.
Okay. Also, Harsh or someone, whoever has the link, just drop the link on the chat once more, I think. And Leap joined a little late and she may not have gotten that link. Okay.
Yeah, I had sent to her on personal.
Okay, sure. Okay. All right, so let's talk about push and pop. Okay, so suppose that, yeah, we have done this, right? So we have checked this particular condition that, okay, the counter value represents 2, right? So now let's say that once we've checked that, okay, the counter value cannot be 2 after one step, we also want to check, okay, can it be 1? I mean, we know that it can be 1, but let's say that this is also something that we're checking, and somehow this is also a bug in our specification, right? So the naive way of doing that maybe would have been to, after this, add another assert that says that, okay, the counter value is 1, right? And then do another check set, right? So now what we're doing is these two asserts are encoding that this is a path with 2 states in it. 1 step path, let's say, or 2 state path. And then this assert is saying that, okay, the counter value is 2 at the end of this path. And then we're checking whether that can happen, right? And now this assert is saying that, okay, the counter value is 1 at the end of this path, and we're checking whether that can happen, right? So now if I run Z3, I want you guys to tell me what will happen, predictions. So the first
Unset.
one, yeah. How many unsets will you get?
1.
Okay, so that is,
there are 2 check sets.
yeah,
right?
there's 2 check sets. So how many unsets will you get? The first one will give us unset because it's just the same thing. But what happens with the next one?
It's also unset because it conflicts with 46.
Yes, exactly. It conflicts with 46, so it is unset. Yeah. So now we are like in a problem, right? So we have to somehow, we are basically in a situation where you have to somehow remove an assert, right? And how do you do that? So there are ways you can like do it just in using like some Boolean trickery. Basically have things like indicator variables, like say something implies this thing and so on. But Z3 and all SMT lib2 compliant solvers have this, most of them, let's say, have this feature called pushing and popping. What this lets you do is basically it lets you treat this table of asserts as a stack, and it can let you push a frame onto the stack. So when I say push, what happens is basically a new frame gets pushed onto this stack, and this assert is now going to sit on this particular frame. Now, when you do check set, this doesn't really matter. The structure of the stacks is basically completely ignored by the check set. Check set is going to just see these 3 asserts, right? And it's going to do it on its own. But now when we do pop, what's going to happen is this last stack frame and all the asserts that was there in that stack frame is going to be popped out, right? So that is essentially going to remove this particular assert that you have. So what you can think of this in terms of coding is that you're setting a sort of a checkpoint over here, and by doing a push, and then you're popping. By doing a pop, you're returning to the checkpoint, right? And since it's like a stack like thing, you can of course do pushes and pushes inside that, and then multiple pops, and you just have to keep track of the stack in your mind or in your code somehow, right? So now if you do this, then you'll see that this should be sat. Yes. Right, and if we can do a get model. Give us some model. Yeah. So it's telling us that, okay, x01 is true, x10 is false, and then just giving us some model. It's probably just there's only one path that this particular transition system can take, that has got one transition in it. So it's just probably printing out that particular path. Yeah. So this is basically how push and pop works. And I had added another push and pop over here. This is just for some symmetry and good practice reasons. But basically that was not strictly necessary. So this is what you can do. So in general, this is actually a very common sort of a framework where you set up your environment in some sense, like your playing field or whatever constraints that your variable can have. And then you have a particular condition that you want to check, right? So you set up your transition system, and so let's say a path in your transition system. And then you have a particular condition that you want to check. And before you check the condition, you just push, like before you assert the condition, and you just push, and then you check, and then you pop, right? Okay. So I think we should leave and rejoin right now. Are there any questions?
Yeah, sure.
if there are any questions, otherwise we'll just leave and rejoin. I think in fact, let me just rejoin, then we'll talk do the questions after
Like
that.
this, we have to join the same link.
No, I'll send another thing to the WhatsApp group. That's why I asked you to send that to the
Okay.
chat.
Okay.
I'll also, of course, I'll also send out a Moodle thing, but I think the WhatsApp group people will be able to see immediately.
Okay.
Is there anyone here who is not in the WhatsApp group and doesn't have a link just before we leave? Okay, so I'm gonna assume that's a no. All right.